Hey everybody, this is Mr. Beckstrom, and today I'm taking a look at an example from homework 4.7. This was number 15, and this one says calculate the limit as theta approaches pi over 2 from the left of 2 cosine, 2 tangent theta raised to the 2 cosine theta. So first thing I'd probably do with this is to see what happens when we get really close to pi over 2 from the left. So what I'm going to do is, I've already put these in here like this. So for my y1, I'll just put in the base here, and for y2, I'll put in the exponent. And then when I go over here, and I already put in a couple, but let's see what's going on. So as I get really close to pi over 2 from the left, so the first thing I'm going to do is I'm going to put second pi divided by 2. And I'm just going to subtract a really small number like 0.01. And I can see that my base is already at almost 200, and my exponent is at around 0.02. It's very close to 0. So let's try the same thing here. And don't forget, make sure you're in radian mode. So pi over 2. And let's get even closer to pi over 2 from the left. So let's subtract 0.000001 and just see what happens. Notice that our base is getting much bigger and our exponent's getting really much smaller. So if we look at the procedure on page 306 for indeterminate forms, we see that this one looks like it's in the form of infinity raised to 0 when we apply the limit from the left. All right, so what does that mean? It means that we can do a little bit of manipulation, rearrangement, and hopefully use this L'Hopital's rule in order to solve. So the first thing I want to do is do a trick like we did for number 14, and that is that we're going to start with e to the natural log. Remember, e to the natural log are inverse functions of each other, so they'll cancel out. So this right here will become the exponent there. So 2 tangent of theta raised to the 2 cosine of theta. And the reason I did this is because, remember, since these cancel out, these two functions are essentially the same, except now we can use the rule of logarithms in order to move this exponent out in front of this natural log here. So this is going to be equal to e to the 2 cosine theta natural log of 2 tangent of theta. Okay, so now remember, we're finding the limit as theta approaches pi over 2 from the left. And if we can look back to, I believe it is theorem 2.12 on page 106, that if we're taking the limit of the outer function for a composite function, and this function is both continuous and differentiable on the interval that we're looking at. So we're looking at it as theta approaches pi over 2 from the left, which it is. We can then find the same function, but with the limit of the inside function. So that's what we're going to do here. So this thing is really going to be equal to e, and then we're going to put the limit up here of theta approaches pi over 2 from the left of this function here. So this is going to be 2 cosine of theta times the natural log of 2 tangent of theta. And now we're really just going to be working on this limit right here. And when we get that limit, then we'll replace whatever value we get, if we get a finite value, with the exponent here and apply e to that exponent. All right, so let's see how we can just look at this function right here in a way that allows us to use L'Hopital's rule. And what I'm going to do is I'm going to do the limit as theta approaches pi over 2 to the left. Now, it may be able to work both ways by putting one of these on the top and one of these on the bottom. But I have found, just through personal history of doing these, that I usually keep the term with the natural log on the top. So this is going to be the natural log of 2 tangent of theta, and on the bottom, and we're going to leave the 2 up there as well. And on the bottom, it's just going to be 1 over cosine of theta, which is secant of theta. Which is secant of theta. All right, now we know that plugging the pi over 2 into the natural log of tangent of theta is equal to, or gets closer and closer to, where I put tangent of theta into y1 here. So it's getting closer and closer to infinity. So let's go over here and actually do a secant of theta and see what happens with that as we get closer and closer to pi over 2. So remember, secant of theta is the same as 1 over sine of theta. So that's how I'm going to do it. 1 divided by sine of x in this case. And enter, and we go here. And we can see that it looks like the bottom is getting closer and closer to 1. And we'll put 1 over cosine of theta, which is equal to secant of theta. And then when I go back here, we see that that is approaching a very large number as well. So this is going to give us the infinity over infinity that we need in order to use our L'Hopital's rule. So now I'm going to find the derivative of both the top and the bottom. So this, it's going to be equal to the same limit here. So make sure I got here. The limit as theta approaches pi over 2 from the left. All right, on the top, that's going to be 1 over 2 tangent theta times the derivative of tangent theta, all times 2 here. And the derivative of tangent of theta is secant theta, secant squared theta, excuse me. So this is going to be 2 times 1 over 2 tangent theta, and then times the derivative of the inside function, which the derivative of 2 tangent theta is equal to 2 secant squared of theta. So that's going to be our top here. And then our bottom, the derivative of secant of theta is secant theta tangent theta. Tangent theta. All right, now let's go ahead and do a little bit of manipulation here and see what happens. All right, so on the top, that's going to cancel out with that. And I'm just going to be left with 2 secant squared theta. So this is the limit, 2 secant squared of theta over tangent of theta. And I'm going to multiply this by the reciprocal of the denominator. So that's 1 over secant of theta tangent of theta. And that will cross out with one of those. And this is going to give me, and I'm going to go ahead and write the, well, let me do it this way first. 2 secant of theta over tangent squared of theta. And now let's go ahead and do this using sine and cosine. So this is going to be 2, and secant of theta is 1 over cosine of theta. And then tangent squared of theta is going to be sine squared of theta. Sine squared of theta all over cosine squared of theta. But we're multiplying by the reciprocal of that. So let me go back here a little bit, sorry. So tangent squared of theta is sine squared of theta over cosine squared of theta, but the reciprocal of that is cotangent squared of theta, and that's going to be cosine squared of theta over sine squared of theta. So that's going to cancel out with that, and we should finally be left with something that we can work with now. So this should end up being equal to 2 cosine of theta all over sine of theta, or sine squared of theta. sine squared of theta. And as theta approaches pi over 2, the cosine of that is going to be 0, right? And the sine of that is going to be 1 squared. So this is just going to be equal to 0. So it's a lot of work, but that's how we get down to the exponent of the e being equal to 0. And then we can just replace that 0 back into the exponent position, and e to the 0 is equal to 1, and we are done. All right, if you guys have any questions at all, let me know, and have a great rest of your weekend. Thanks.